The truth of the matter is emerging technology may develop distillation properties that are better than petroleum. Other properties, again with our AMJ fuel, is energy density, freeze point, and greenhouse gas emission projections. Okay, energy density, the comparison is Jet A, the coal to liquid, the SPK type fuels, and then of course the AMJ 700 candidate fuel. And you see that the sugarcane jet fuel is high, has the equivalent density of petroleum. If you look at freeze point, at which point does the fuel begin to gel or not flow? At what point does it become not liquid? Okay, and I think this is where this is a high quality aspect that we can improve petroleum. You see petroleum JP8 fuel begins freezing around minus 52 degrees C. That's quite cold, but up in elevation, typical. Okay, you see CTL is a little bit colder, but you could see that AMJ 700, when we ended the test, or I should say when the Air Force, the U.S. Air Force ended the test at minus 70, the fuel was still liquid. Okay, so not only is it superior to petroleum, it will provide blending improvements to petroleum. And then greenhouse gases, you see the tremendous benefit of a sugarcane-derived jet fuel. Another set of data to give you what you can expect from a cane-derived aviation fuel. 3 fit-for-purpose metrics for fuels: viscosity, sulfur, and lubricity. Lubricity is a measurement of how abrasive is the fuel on fuel components. Sulfur, I think we're all familiar, is sulfur emissions. And then viscosity is a fit for purpose. How well can you atomize the fuel? How well will it operate with the fuel system? And you see with lubricity, once again, we have superior lubricity properties compared to petroleum. Once again, makes for a good additive improvement to petroleum. Nearly zero sulfur, and viscosity is slightly lighter in our current formulation. It does improve atomization, but once again, we're subject to meet petroleum viscosity simply because that's the benchmark. Some combustion tests, ground engine tests that were performed by GE Aviation in the United States. This is a little bit of a difficult chart to understand, so I'll explain it because it does have very impactful results. Let me first read. The text reads is that during lean blowout, that is, when does the engine stop running, does it blow out due to lean conditions? And those of you not familiar with that situation, it is a situation that engine manufacturers are very sensitive to, because you can understand as an airplane is descending on landing, the air density is increasing, therefore it's getting leaner, there's more air, but it's also at the same time that the throttle is being removed from the engine, obviously load. So you have a very sensitive situation of low load and increasing lean. So the engine manufacturers want to understand at what point relative to petroleum does the lean go out, or does the engine go out, okay? And what we found here, what GE found is under 3 different engine conditions, these numbers 6%, 4%, 2% are the differential pressures in the engine. And perhaps the GE representatives in the audience could give a better explanation than I can, but they basically are pressure differentials that an engine will see in flight. Okay? And what we have here is a couple of SPK type fuels, AMYRIS AMJ 700 at 50%, the C10s at 100%, 50% 310, and then 10% 310. These are conditions that the Air Force actually asked GE to perform the test. What you see here, if we look at simply the orange 700, is that on this graph, this is basically petroleum is in the middle. If 0 means no change to petroleum, it works, it behaves just like petroleum. To the right is, I refer to it as improvement needed. That is, the lean blowout occurs sooner than petroleum, which is not good. Okay? On the left side, I call it better. That is, you actually could go leaner than petroleum, which is good. The engine keeps running. Okay, and what you'll see for the cane-derived AMJ 700 fuel is in these two conditions, AMYRIS jet is far superior to petroleum and superior to a couple of early renewable jet fuels that have been validated already. Now down here, yes, again, this is a development data. We have slightly earlier condition of blowout than petroleum, but compared to these fuels that have been already validated by ASTM and DEFSTAN, we're actually better. Okay, so very powerful results here, again showing that we are potentially superior to petroleum. Another set of engine testing is another condition called light off. So if the engine does go out, lean blowout, how quickly will it start again? In similar type format, so I would quickly summarize the conclusion, is that with AMYRIS jet fuel, it always starts quicker than petroleum, easier than petroleum, and that's what you see here, here, and here, always better than petroleum. And then you see in this case, superior to renewable jets presently validated. EMBRAER already discussed our flight. We do have a demonstration flight in cooperation with Azul, EMBRAER, GE. We are to have an instrumented flight early in the year, next year, 2012, and then a demonstration flight summer of 2012. The deliverables of the project is material compatibility data from wing to engine performance data, instrument flight results, and then a sustainability report on the AMYRIS jet fuel. All this data will be used and contributed to the ASTM and DEFSTAN validation process. And to conclude, the AMYRIS Total Alternative Aviation Fuel Project will yield suitability, which will mean in terms of compatibility with Jet A and A1 fuel requirements. It will have drop-in fuel qualities so that it's transparent throughout the industry. It will have sustainability from a standpoint of low greenhouse gas, and it will be sustainable through sugarcane derived in Brazil, and through a partnership like Air Total have global distribution. Bom. Obrigado.
Thank you. Why don't we have you guys join us, all four of you. Come on up on the panel. Obrigado. I think we've got nameplates, so just make sure you're sitting where you're supposed to be sitting. And we're going to give everybody an opportunity to think up of questions. I've got a few here, and I'm going to use the prerogative of the chair to allow you guys to ask questions even of each other. But the first one, I guess, is since I spent the last 3 years at Unica, and I sometimes in Brazil am asked this, is actually a question somebody asked in the audience, an unnamed person. It says, why don't we just use ethanol in these planes? I know the answer, but I'm going to let you, the experts, give it. So maybe our two aircraft manufacturers, Jim and Guilherme, do you guys want to answer? Why not just ethanol?
Well, it's what I have to said in my presentation. Our engines and airframes have been designed to run around petroleum-based fuel. And as we move away from petroleum-based fuel, then that's the type of molecules that are petroleum-based fuel, then that means we have to totally recertify all our engines and all our airframes, and the cost of doing that is extremely expensive. So that's why we could design engines and airframes that run under different types of fuels, but the cost to do that would be very prohibitive.
Yes, ok, português. Eu concordo com o Jean no sentido de que realmente os aviões, eu também comentei isso na minha apresentação, que os aviões que hoje voam aproximadamente 20 mil aeronaves movidos a jatos, né, já estão a querosene, então fica difícil a gente fazer uma mudança. isso seria muito caro e, além disso tudo, a gente não tem etanol no mundo inteiro para mover esses aviões. Como a gente não consegue uma solução flex para os motores e aviões, nós temos que fazer esses combustíveis flex. Porém, no caso do Brasil, né, muitos de vocês já sabem que a gente no Brasil, a própria Embraer, já certificou um avião, um pequeno avião, quer dizer, um avião a pistão, quer dizer, uma solução muito local, uma solução muito de nicho, que é o Ipanema, que é o primeiro e único avião certificado e serializado no mundo para a utilização do etanol, que é uma vitória, eu acho que para a gente, para o Brasil, porém, infelizmente, a gente não pode fazer uma utilização global. Como a gente está falando de assuntos globais e necessidades globais, a gente tem que manter realmente a pequena necessidade do cálculo. E por que exatamente? Né? Pela questão da termos técnicos. Por quê? Porque o etanol, ele, além da compatibilidade de materiais, ele tem uma certa questão de potência, de range, e aí, por consequência, você precisaria de mais combustível para você fazer um voo longo, então você poderia utilizar isso para um voo de curta duração, aí você até conseguiria em termos do formato do avião atual. Você tem toda a questão também do ponto de congelamento do combustível, quer dizer, um avião poder voar a 30, 40 mil pés não dá com etanol. Porém, mas se você for voar a 20 mil pés, a 25 mil pés, talvez ainda dê. E aí, inclusive, são coisas que são analisadas, tanto a Embraer quanto algumas entidades brasileiras estudam como seria o impacto da utilização do etanol para aviões pequenos, mas de uma forma muito pontual aí. Eu acho que é uma coisa que, para o futuro. No futuro a gente tenta isso.
Bom, a minha explicação é ainda mais simples. Eu até testei com eles, que se for andar em etanol, a fuselagem do avião teria que ser o tanque de combustível e os passageiros teriam que ter na asa, porque o combustível necessário para o avião usando etanol seria muito. E se tem alguma dúvida, o John Ingram aqui, se usa checar o consumo da turbina que ele usou usando etanol, funciona uma beleza, mas haja cana. Uma outra pergunta que essa até eu mesmo faço Charles, você falou, salvo engano, falando do custo dos combustíveis, que, no final das contas, para as companhias aéreas, o combustível acaba custando, acho que a cifra que você usou era 40%, talvez, do custo operacional, o combustível. Se o combustível é tão importante para a companhia aérea, por que a companhia aérea, na realidade, não investe em biocombustível, em combustível para aviação, ou ela investe nisso? E aí eu deixo os outros panelistas, talvez, para sugerirem respostas.
Yeah, it's true. The fuel cost was traditionally a very small element, and nobody really cared about it. It went up to 40%. But what is really killing the airlines is today you make money if you are a good gambler. Airline executives should go to Las Vegas and learn gambling, because airlines today lose or make money with hedging. If the fuel price goes to $300 a barrel and stays there forever, then the world would adapt, and then the ticket will be more expensive. But if it is oscillating from $147, then down to $30, then back up to $120, now around $90, what's next? So volatility is what makes it difficult. The other question in terms of going into vertical integration and going into fuel production or going into participation, well, that is another theme, because you can argue in different areas. Airlines have actually gone the other way. They went back to the core business, sold their duty-free, sold their handling operations, sold usually what was profitable. But airlines are really in the business of flying passengers and cargo. So I think that some airlines are working with the industry and do tests like we see here the example, but it's not their business.